This video is going to cover the solutions to the tutorial problems for the third topic, how does a hot air balloon work? Problem 1. In this problem, we're told that Fiona has a mass of 65.0 kilograms and we're asked to calculate her weight on a variety of planets. So remember, weight is a force and the weight force can be calculated using weight is equal to mass times the acceleration due to gravity on the surface of that planet. So part A asks us on Earth and we're told that G is 9.8. So Fiona's weight on Earth is 65.0 times 9.80. Solving that on the calculator, we get 637 newtons is her weight on Earth. In part B, we're asked to calculate her weight on the Moon. So on the Moon, she's still got a mass of 65 kilograms, but the acceleration due to gravity is 1.62 meters per second, and so this gives her a weight of 105 newtons. We're then asked on Mars. So on Mars, she still has a mass of 65 kilograms, but the acceleration due to gravity is 3.72 meters per second, and so this gives her a weight of 242 newtons. And finally, we're asked on Jupiter, where she's once again got a mass of 65 kilograms, but the acceleration due to gravity is 26 meters per second, and so she's got a weight of 1,690 newtons. So then the question asks us, how would Fiona feel when she was standing still or jumping on these planets? Well, you know how you feel when you're standing still on Earth. On the Moon, you'd feel a lot lighter because there's a lot less force pulling you towards the surface of the Moon. The same on Mars. And then on Jupiter, you'd feel a whole lot heavier because the force between you and the surface of the planet is a lot greater. If you tried to jump on the Earth, you know how high you can jump, around about 20 centimeters or so. On the Moon, you'd be able to jump a lot higher because there's a lot less force pulling you back down to the surface. On Mars, again, you'd be able to jump a lot higher, though not quite as high as on the Moon. And on Jupiter, it would be very hard to jump. You wouldn't reach such a high height because there's a lot greater force between you and the surface of the Moon. So you would feel heavier on Jupiter and lighter on Mars and the Moon. Sorry, rather than you, it's Fiona. And Fiona could jump higher on the Moon, slightly less high on Mars, and not very high on Jupiter. Problem 2. So you have a ping pong ball and a golf ball, and you're asked if you drop them, would they hit the ground at the same time on Earth? So golf ball, ping pong ball, if you dropped them on Earth, the golf ball would hit the ground first and then the ping pong ball would hit the ground second. So on Earth, the golf ball would hit the ground before the ping pong ball. This is due to air resistance. The ping pong ball has less mass and So the air resistance force is greater as a fraction of its weight force, causing it to accelerate more slowly and hit the ground after the golf ball. So now on the moon, there is no atmosphere. So if you were to drop them from the same height on the moon, they would hit the ground at the same time, as there is no air resistance. Air resistance is caused by the atmosphere. So on the moon, they would hit the ground together. Problem 3. This says that studies in New York have shown that cats are more likely to survive a fall from the 45th floor apartment than from the 7th floor apartment. Can you use physics to explain this observation? So what happens with the cats is that when they fall out of the apartment building, they feel the weight force downwards, which causes them to accelerate down towards the ground, and they feel an air resistance force upwards. Now this air resistance force is actually dependent upon their speed. So the faster they're going, the greater the air resistance force. So the cats will speed up until the air resistance force is the same size as the weight force. When this happens, they travel at a constant speed. And this speed has a special name. It's called their terminal velocity. So cats falling out the 7th floor just managed to reach their terminal velocity. So it takes approximately 7 floors for the cat reach its terminal velocity. So cats falling from the 45th floor have same speed on impact as those falling from 7th floor, but more time in the air to prepare for the crash landing. So they are in fact more likely to survive from above the 7th floor. Problem 4. So this problem says, describe what forces act on the parachuter when they jump from a plane. How do the forces change when the parachuter opens their parachute? Can you describe how this is related to the acceleration and speed of the parachuter? And yeah, we'll be doing more on acceleration and speed in later topics. So this is really just a preview of that topic. Okay, so when the parachuter jumps out of the plane, initially they don't open their parachute. They fall like this. They have the weight force acting down and they have the air resistance force acting upwards. So when parachuter initially jumps, they accelerate due to their weight until they reach their terminal velocity, which occurs when air resistance force is the same magnitude as the weight force. Now the parachuter opens their parachute. So here they are. Here's the parachute. The parachute has a large surface area. And so this increases the air resistance. And it will slow them down. So when parachute is opened, the air resistance increases, and this slows them down. To a new terminal velocity, which is less than without the parachute. Now let's just quickly draw a graph showing what's happening. Here's the acceleration, here's the time. So initially they have the weight force and the air resistance. So the acceleration starts off at a large value and drops off. And then when they open the parachute, there's a large air resistance. So the acceleration's actually negative for a little amount of time and then goes back to 0. Sorry, that's a bit messy, but the acceleration's decreasing and then it becomes negative when they open the parachute because they're actually slowing down a bit. And so the speed or the velocity with time, they start off with no speed. The parachute reaches a terminal velocity with the parachute, without the parachute, and then when they open the parachute, they slow back down to a new terminal velocity. So the velocity or speed time graph is going to look something like this. Problem 5. We're asked to calculate the density of a 20-cent coin. So to do density, we need to use density is equal to mass over volume. Now we're told the mass, but we're going to have to work out the volume of the coin. So we've got a coin, looks like this. It's got some height h and some radius r. So the volume is equal to the surface area, which is the area of a circle, pi r squared, times the height. That is the formula for the volume of a cylinder. But we're not told the radius, we're told the diameter. So the radius is equal to the diameter over 2. So we're told that the diameter is 23.4 millimeters, and so the radius is equal to half of that. Which is 11.7 millimeters, but let's do this in centimeters, so it's 1.17 centimeters. Okay, so the volume of our 20-cent coin is pi times 1.17 squared times the height, which is 2.2 millimeters or 0.220 centimeters. So solving that, we get 0.946 centimeters cubed. And so the density is equal to 11.3 grams over 0.946 centimeters cubed. And so this is equal to 11.9 grams per centimeter cubed. Problem 6. In this problem, we're told that you mix olive oil, water, a lump of beeswax, a stone, and a cork in a jar. And we need to draw a labeled diagram showing as many details as we can about what the mixture would look like. So here's our jar. Now what we're going to have is we're going to have the oil floating on top of the water. So we'll have the water down the bottom and we'll have the olive oil here, and it will happen that way around because the olive oil is less dense than the water. So the density of this is 1,000 kilograms per meter cubed, and of olive oil it's 880 kilograms per meter cubed. Now we have a stone which has a density of 2,500 kilograms per meter cubed. So that's more dense than both the olive oil and the water, and so the stone will sink to the bottom and then down here. Now the beeswax has a density of 960 kilograms per meter cubed. So that is somewhere between the water and the olive oil. So the beeswax is going to float on top of the water. But we can actually work out more details because when it floats, here's the beeswax, here's the water, and here's the oil. It's got its weight force downwards, and it's got the buoyancy force upwards. And let's call this part of the volume VOO, volume of olive oil displaced, and here we can say VW, the volume of water displaced, and we'll call the total volume of the beeswax VBW. So we know that the volume of beeswax is equal to the volume of the olive oil displaced plus the volume of the water displaced. The other thing we know is that this weight force has to equal this buoyancy force. So we've got that the weight force of the beeswax is the density of the beeswax times the volume of the beeswax times the acceleration due to gravity, and that's equal to the weight of the water displaced, which is the density of water times the volume of water times g, plus the weight of the olive oil displaced. So that's the density of the olive oil times the volume of the olive oil times g. So these g's cancel each other out, and we can replace this volume of beeswax with the volume of olive oil displaced plus the volume of water displaced, and we have numbers for these things which we can substitute in. So we've got 960 times the volume of the olive oil plus the volume of the water displaced is equal to 1,000 VW plus the density of the olive oil, which is 880 times V olive oil. So let's move the olive oil terms over to this side. So 960 minus 880 gives us 80 times the volume of the olive oil is equal to 1,000 minus 960, so that's 40 times the volume of the water. So this tells us that the volume of the water over the volume of the olive oil, so dividing this by this, we end up with 2. So the volume of the water displaced is twice the volume of the olive oil displaced. So to draw this really accurately, our beeswax is going to float here. And we'll have 2/3 of it below the water and 1/3 of it above the water in the olive oil, like that. So 2/3 in water, 1/3 in olive oil. And then finally, we've also got a cork. So the density of the cork, we're told, is equal to 220 kilograms per meter cubed. So that's much less dense than all these other ones, so it's going to float on top. But once again, we should work out what fraction is below the water to be as accurate as possible. So once again, we've got that our buoyancy force is equal to the weight force. So the buoyancy force in this case is the weight of the olive oil displaced. So it's the density of the olive oil times the volume of the olive oil displaced times G, and that is equal to the weight of our cork, which is the volume of the cork times the density of the cork times G. So these G's will cancel out, and we know that the volume of the cork over the volume of the olive oil displaced is equal to the density of the olive oil, which is 880, over the density of the cork, which is 220, so that is equal to 4. So the volume of the cork is equal to 4 times the volume of the olive oil displaced. So we've got 1/4 of the cork below the olive oil and 3/4 above. So this is the cork, 3/4 above olive oil and 1/4 below olive oil. And so that is a fully detailed diagram showing what the system would look like. Problem 7. So in this problem, we're told that ice has a density of 0.9167 grams per centimetre cubed. So we've got a lump of ice here. It's got a density of 0.9167 grams per centimetre cubed. And seawater has a density, so here's our ice block, here's our seawater, and it has a density of 1027 kilograms per metre cubed. And we're asked to calculate what percentage of an iceberg will float above sea level. So what percentage of the iceberg is this part here? So to answer this problem, we're going to need to use Archimedes' principle. So we know that the weight force is equal to the buoyancy force. And so the weight force is equal to the density of the ice block times the volume of the ice block times the acceleration due to gravity. And the buoyancy is caused by the displacement of this water here and is equal to the weight of the seawater displaced. So this is equal to the density of seawater times the volume of the seawater displaced times G. So the G's will cancel each other out, and we can rearrange this now to get that the volume of the seawater displaced over the volume of the iceberg is equal to the density of the ice over the density of seawater. And we've got numbers for these things. So this is equal to 0.9167 grams per centimetre cubed over 1027 kilograms per metre cubed. Now our problem is that these two things are in different units. So let's convert this density up the top, the one for the ice, into kilograms per metre cubed. So to convert it into kilograms, we'll need to times it by 10 to the minus 3. And then to convert it from per centimetre cubed to metres cubed, we'll need to times it by 10 to the 2 and cube that. So to get from centimetres to metres, we need to divide by 10 to the minus 2, but this centimetres is on the bottom. So that's divided by 1027. So this is equal to 916.7 over 1027. And so solving this, we get 0.8925. So what this is telling us is that if we've got 89.25% of the iceberg below the water, because the volume of the seawater displaced divided by the volume of the ice is equal to 0.8925. So we've got 89.25% is below the water. But the question asks us how much is above, so we'll need 100 minus 89.25, which gives us 10.74 is above the water. And so that's how you do that one. We got the 0.74 because I kept all the significant figures in the calculator. If you just type this part into the calculator, you'll end up with 10.75. If it was an exam, then either one would be marked as correct. Problem 8. We're told that the pressure inside a gas bottle is equal to 350 atmospheres. And we're told that that's at room temperature, so that's at a temperature of 25 degrees C. And we're told that now the gas bottle is placed in a fire at a temperature of 600 degrees C. And we're asked, what is the pressure inside the gas cylinder now? So to answer this one, we're going to need to use the ideal gas law. We've got PV is equal to nRT. Now, we're changing the temperature, but the volume of the gas cylinder is not changing. So this part's constant. We're not moving gas in or out of the gas cylinder, so N is constant, and R is a constant. It's 8.314. So the only two things which are changing are P and T. So we can write P on T is equal to a constant, or we can write this as the initial pressure over the initial temperature is equal to the final pressure over the final temperature. Now we're asked to calculate what's the final pressure inside the gas cylinder. So we can write that the final pressure is equal to the initial pressure over the initial temperature times the final temperature. And now we can substitute everything in. Now if we're happy to get our final pressure out in atmospheres, we can leave this initial pressure as atmospheres. So this is 350 atmospheres. Now the initial temperature, that's the room temperature, but because we've used the ideal gas law, we need to convert all our temperatures into kelvins. We can't just substitute it in degrees Celsius. So hopefully you remember from the last topic, to convert from degrees Celsius to kelvins, we have to add 273. And then the final temperature is 600 degrees Celsius, so we add 273 to that. So solving this on the calculator, we end up with 1025, and we're going to give it to three significant figures. So we write this as 1030 atmospheres is the final pressure. So the question then goes on, suggest a possible consequence of this increase in pressure. Okay, so this pressure is getting quite large. The pressure actually means that there's a large force on the air, on the surface area of the cylinder, on the walls. And so that large force can actually cause the gas bottle to explode. So this is why people need to be very careful when they store their gas bottles. You don't want to store it in an area where it could undergo a rapid increase in temperature, because this can cause it to explode, which can be very dangerous. These gas bottles form a lot of shrapnel, and that does a lot of damage when they explode. Problem 9. So we're told that a weather balloon works a little differently from a hot air balloon. In a hot air balloon, the gas is heated and the air molecules are free to move in and out of the balloon. A weather balloon is more like a helium balloon. The number of molecules is fixed and the gas inside is less dense than the surrounding gas. Okay, so here we've got a weather balloon like this. So these are used to take instruments into the upper atmosphere to make measurements. And this one here is filled with hydrogen. And we're asked to calculate the maximum mass a weather balloon can lift. So it's carrying some mass up if its volume is 2.3 meters cubed. So the volume is 2.30 meters cubed, and we want to know what mass can it lift. And we're told that the density of the hydrogen is equal to 0.0899 kilograms per meter cubed. And the density of the air outside is 1.22 kilograms per meter cubed. So this is the density of the air. And we're told that the mass of the balloon is equal to 600 grams, so 0.60 kilograms. Okay, so to answer this one, we're going to need to use Archimedes' principle again. So here's our buoyancy force. And here's our weight force. And these two things are equal, so weight force now the weight force, we've got the mass of the balloon times g. It's also got to lift this helium, so plus the density of the, hydrogen, not helium, the density of the hydrogen times the volume of the balloon times g. And finally, it's got to lift this load as well, so plus mg. And this is equal to the buoyancy force, which is the weight of the air that it displaces. So this is equal to the density of the air times the volume of the air times g. Now g occurs in every term, so we can cancel that one out. And what we're trying to find is this mass here. So we've got that the mass that it can lift is equal to the density of the air times the volume, minus, we move this over, the density of hydrogen times the volume, minus the mass of the balloon. And now we've got numbers for all of these, so we can substitute in. So we've got 1.22 times 2.3 minus 0.0899 times 2.3 minus 0.600. And so solving this on the calculator, we get 1.99923, but we should only give it to 3 significant figures. So this is 2.00 kilograms is the mass that this balloon can lift. So problem 10. So we're told a hot air balloon has a volume of 2,500 meters cubed. Okay, let's draw a hot air balloon. So the volume is equal to 2,500 meters cubed. The balloon and its load have a mass of 500 kilograms. The density of air at 20 degrees C is 1.20 kilograms per meter cubed. And in part A, we're asked what density of air is required inside the hot air balloon in order for the balloon to lift off the ground. So for this one, we're going to need to use Archimedes' principle. We'll need to equate the weight force and the buoyancy force. And so the weight force is equal to mg plus we've got the mass of the air inside the balloon. So that is equal to the density of, let's call it rho b in here to symbolize the density inside the balloon times the volume of the balloon times g. So this is the weight, and that has to be equal to the buoyancy force. And so that is equal to the weight of air displaced. So that's the density of air times the volume times g. So this is the buoyancy. So these g's will cancel each other out. And what we're trying to do is work out what's the density of the air inside the balloon. So we've got that the density of air inside the balloon times v is equal to the density of air times v minus m. And so the density of air inside the balloon is equal to the density of air in the balloon v minus m over the volume. So now we can substitute everything in. We've got 1.2 times 2,500 minus 500 over 2,500. So 1.2 times 2,500 is 3,000 minus 500 over 2,500. So 2,500 over 2,500, which is equal to 1.00 kilograms per meter cubed, is the density of air that we need to get inside this balloon. Now part B says, assuming atmospheric pressure, what temperature does the air inside the balloon need to be heated to in order to achieve this density? So we know that density is equal to mass over volume. So the mass of the air inside the balloon is equal to the number of moles times the molar mass of the air over the volume. Now what we're going to need to do is use the ideal gas law. So the ideal gas law tells us that PV is equal to nRT. So we can rearrange this to get N on V by dividing by V is equal to P, and then we'll need to divide by RT. So we can replace this N on V with P on RT. So that tells us that the density inside the balloon over the density of air is equal to the pressure inside the balloon over R, the temperature inside the balloon, times the mass of air. So that's replaced the NV with the PRT for the balloon over the pressure of the air over R times the temperature of the air times the molar mass of air. Now almost everything here cancels out. The molar mass of air is the same inside the balloon and outside the balloon. So these ones cancel. R's cancel. Now the pressure is actually the same inside as outside. We've got atmospheric pressure inside because this is open to the air so that the air molecules can move in and out. So that cancels. So we've got the temperature of the air over the temperature of the balloon. So this is what we're trying to find. We've got the temperature of the balloon is equal to the temperature of the air times the density of the air over the density of the balloon. And so the temperature of the air, that's 20 plus 273 kelvins, because remember this was at 20 degrees Celsius and we need to convert to kelvins. So then times the density of air, which is 1.20, over the density inside the balloon, which is 1.00. And so solving this one on the calculator, we get 351.6 kelvins, but then we subtract 273 from it and we end up with 78.6 degrees Celsius. So that's how warm you have to heat the air in here to achieve this density and allow that hot air balloon to take off.